In this video, we will try to solve a problem on expansion path. The question is like this. When production function for a firm is given as Q is equal to 20 into K to the power 0.5 into L to the power 0.5, where Q is the quantity, K and L are capital and labor. Price of capital is $5 per unit and price of labor is $4 per unit. What will be expansion path ratio for the firm? Options are given as these are the options given. Okay, so what do we mean by the expansion path? Actually, if I draw the isocount here, so we have labor, units of labor here, units of capital here. Okay, by expansion path there we mean a path connecting optimal input combinations as the scale of the production expands. Okay, if this is our isocost line, okay, and if this is our isocount, okay, and similarly if we have another, let us say, isocost line like this, and we have another isocount, let us say this, expansion path is a path connecting these optimal points. Okay, so we can have another isocost line, and corresponding to this we will have another isocount. So this is iq1, this is isocount second, isocount first. When we join these optimal combinations, we get the optimal, what we call the expansion path. Okay, now where does this occur? It occurs at the point of tangency between isocount and isocost lines. Okay, so how can we calculate here what we are being given? We are being given Q is equal to 20 K to the power 0.5 L to the power 0.5. Okay, and price of capital is 5. Okay, let me write it like this. P subscript K means price of capital is 5 and price of labor is 4. Okay, now to get the optimal pointers, that means these are our optimal pointers, the condition that should be satisfied, that is the isocount should be tangent to the isocost line at that time. Okay, that means we say slope of isocount, by slope of isocount we mean the marginal rate of technical substitution between labor and capital should be equal to slope of isocost. Okay, isocost line. Okay, by isocost we mean the ratio of the prices of capital and labor. Okay, how do we get this marginal rate of substitution? It is being given by marginal productivity of labor upon marginal productivity of capital. Okay, marginal product of labor upon marginal product of capital means our marginal rate of technical substitution should be equal to what we call it wage rate upon rental rate of capital. Okay, so what is marginal product of labor? That means we need to differentiate this very function partially with respect to L first. Okay, if we partially differentiate this with respect to L, what will we get here? So let me write it here first. So our MPL means the partial derivative of our production function with respect to L. Okay, if we partially differentiate this with respect to L, so 0.5 will become coefficient. So we have 0.5 into 20 L to the K to the power 0.5 L to the power 0.5 minus 1 by rules of by power function rule. Okay, so 0.5 into 20 comes out to be 10 K to the power 0.5 L to the power 0.5 minus 1 comes out to be minus 0.5. Okay, so this is our MPL. What is our MPK? So let us calculate the MPK again. So MPK will simply mean the derivative of our production function, partial derivative of our production function with respect to capital this time. Okay, so differentiating this with respect to K, so this 0.5 will become coefficient. So we have 0.5 into 20 K to the power 0.5 minus 1 by power function rule, and we have L to the power 0.5. Solving again, 0.5 into 20 means 10. K to the power 0.5 minus 1 comes out to be minus 0.5, and we have L to the power 0.5. Okay, I hope I'm making myself clear. Now using this condition, and what is our wage rate? Wage rate means price of labor, that is 4 here, okay, upon what is the rental rate of capital, that means price of capital, or is our 5 here, okay. Using this condition, now this is our marginal product of labor, this is marginal product of capital. So using this equation, now our MPL is this thing, so I can write it like this. Let me write it like this. We have 10 k to the power 0.5 L to the power minus 0.5. To this we divide marginal product of capital, that is 10 k to the power minus 0.5 L to the power 0.5 should be equal to W upon R, that means 4 upon 5. Okay, 4 upon 5. 10 and 10 will get cancelled. Okay, we can do one thing here. If I transpose this k to the power minus 0.5 to numerator, it will get multiplied with this k and the sign of the exponent will change. Okay, so I can write it like this: k to the power 0.5. If I transpose this here, it will remain k to the power plus 0.5. Okay, when we change denominator to when we transpose denominator to numerator, the exponent sign gets changed. Here it was minus 0.5, it became plus 0.5. Okay, similarly we have here L to the power 0.5. If I transpose this here, okay, so it will get multiplied this L, but the exponent sign will get changed. If it is here minus 0.5, it will become plus 0.5. Okay, should be equal to 4 upon 5. Now bases are same, we can add up the exponents. Okay, so we can write it like this: k to the power 0.5 plus 0.5 upon L to the power 0.5. Again we have same basis, we can add up the exponents. 0.5 should be equal to 4 upon 5. Okay, 0.5 into 0.5 becomes 1, so we have k upon L should be equal to 4 upon 5, which implies k is equal to, transposing this, it will get multiplied. We have 4 upon 5 into L, which implies k is equal to 4 upon 5 comes out to be 0.8 L. Okay, so the correct option should be our expansion path ratio is equal to k should be equal to 0.8 L. Okay, so this option is correct. Thank you. I hope I make myself clear.